Alright, here's our video for lesson 10.4 where we're going to talk about inscribed angles. And we're going to explain what that means, give you some new terminology here. There's not a lot of vocab to write down in the notes, but you will want to place these vocabulary terms in your vocab notebook. They do belong in there. Notice we have skipped lesson 10.3. We're going straight into lesson 10.4. Alright, now we've been talking a lot about circles and about angles and chords and arcs and all these other terms. So far, before this lesson, all of the angles have been with a vertex at the center. Well, now this is our first lesson where we no longer put the vertex of the angle at the center of the circle, but we put the vertex of the angle somewhere else. We put it on the circle somewhere else. You can imagine it like this. Previously, we have been looking at circles like a pizza, and every time we create a central angle, we are cutting to the center. Well, now it's like we're cutting a slice of the pizza all the way to a far side of the pizza, so it doesn't go to the center. So it's like it's a little bit different. So the angles are going to change a little bit. So let's talk about some of the terminology. Notice that the angle formed by each of these segments, I call them streamers in this application, appears to be congruent no matter where point P is placed. All right? What we get is called an inscribed angle. When we have an angle that has a vertex on a circle and sides that contain chords, that's called an inscribed angle. Remember, the word inscribed means drawing something inside. So I'm going to create an angle where the vertex of the angle is on the circle and these two other endpoints of these segments are on the circle, making them chords. So if I put two chords that intersect at a common endpoint, we get what's called an inscribed angle. We can say that that inscribed angle has an intercepted arc. An intercepted arc has endpoints on the sides of an inscribed angle, and it lies on the interior of the inscribed angle. Okay, so that's an intercepted arc. So in circle C, we have a minor arc QS that is intercepted by angle QRS, which is the inscribed angle. So there's a lot of different cases. Case 1 is where the center of your circle is on a side of that inscribed angle. That makes one side of the inscribed angle a diameter. And case number 2, where the center is in the interior of the inscribed angle. Or case number 3, where the center of the circle is in the exterior of the inscribed angle. All right? In any case, we have what's called the inscribed angle theorem, regardless of which case it is. If an angle is an inscribed angle in a circle, then the measure of that angle is half the measure of the intercepted arc, not equal to it. If I had this central angle, if I drew this central angle, that angle measure would equal this arc measure. But notice that this angle measure is much greater than this angle measure at 1. This appears to be an obtuse angle. This is an acute angle. So when I stretch the sides back to the far side of the circle, that angle becomes smaller by half as much. So we can say the measure of angle 1 is 1/2 the measure of arc AB, or we could say the measure of arc AB is twice the measure of angle 1. Okay? So in our example 1, we're going to use these two circles for these two separate parts. In this example 1, part A, they want to find the measure of angle P. Well, we have the measure of angle P here, which has the intercepted arc MN. You'll remember that the angle is half the intercepted arc. So the measure of angle P is 1/2 the measure of arc MN. You don't have to write that every time though, because it's just 1/2 of 70 degrees. 1/2 of 70 is 35 degrees. So the measure of angle P is 35 degrees. Okay? But for part B of this, they want the measure of arc PO. So they want the measure of this arc. This arc is intercepted by angle PNO. So we're just looking at this wedge. So remember that the measure of this angle, which is 56 degrees, is half of the measure of arc PO. Excuse the interruption from the intercom, sorry. So that means I take 56 times 2 to get my answer, because I would double that to get the arc. The arc is bigger than the inscribed angle. And 56 times 2 is 112 degrees. So the measure of our arc PO is 112. Okay, let's try another one. In this example 1a, we're looking first for the measure of arc CF. So I'm going to show you that one, measure of arc CF. That arc is intercepted by angle CDF, which is a 40-degree angle. So all we have to do is take that angle of 40 and multiply it by 2 to get the arc measure. 2 times 80 is 160 degrees. So if you know the angle and are going to the arc, you multiply by 2. If we know the arc, as we do in this next part, and are looking for the angle, measures of angle C, we know this arc is 98, so we divide by 2 to go backwards. So the measure of angle C is 98 over 2, and 98 over 2 is 49 degrees. All right, that creates another theorem for us. Let's pretend that we have one circle where I have two inscribed angles. We have an angle at C, okay, and that intercepts arc DA. But we have another angle at B that also intercepts arc DA. It's the same arc. Since they intercept the same arc, they have to be the same angle measure because they're both half of the same number. So that's our theorem. If two inscribed angles of a circle intercept the same arc or congruent arcs, then the angles are congruent. So angles B and C are congruent because they're both intercepted by the same arc DA or AD. Okay, so we can use that for some problem solving. Here's our first part of example 2. Now we want to find the measure of angle T, and then we also want to find the measure of angle S given this information. So let's do this one part at a time. First we want to find the measure of angle T. Notice that angles T and U are both intercept arc SV. So they have to be equal to each other. Okay, so we can set these two values equal. 3x minus 5 equals 2x plus 15 because they are congruent angles. And then we solve for x by subtracting 2x from both sides, and then adding 5 to both sides. So x is 20. So we need to find the measure of angle T. So we're going to plug in 20 for x. 3 times 20 is 60. And then don't forget to subtract 5. 60 minus 5 is 55. So the measure of angle T is 55 degrees. We would get the exact same value for the measure of angle U if we plugged in 20 here. Okay? But then in part B, we want to find the measure of angle S, or I'm sorry, if the measure of angle S is 3x and the measure of angle V is x plus 16. What I want you to notice is that angle S and angle V are intercepted by the same arc TU. So those are equal to each other again. So our equation is very simple. 3x also equals x plus 16. We'll get a different value of x this time. Solve this for x. Pause the video if you need more time, but this is what you should get. Okay, x is 8. Okay, because if 3x equals the same as x plus 16, x has to equal 8 when we solve it. We're going to plug that in for x to find the measure of angle S. Instead of x, we write 3 times 8, which is 24. That means the measure of angle S is 24 degrees. All right, moving right along, you'll notice that horrible 5-letter word, proof. Don't worry about it. We are going to do this in class. We're going to wait and do the proof in class. It takes a little bit more time. We will do it. Don't Don't freak out yet, but we will do this in class. We're going to skip over it for the purposes of the video, though. All right, so that leads us to our next theorem, that if we have an inscribed angle of a triangle that intercepts the diameter of a semicircle, that's if and only if the angle is a right angle, which comes back from things that we've already talked about. Okay, this has to be a right triangle, so that has to be a right angle because it intercepts a semicircle. All right, so in example 4, we can look at this to find the measure of angle F. FH has to be a diameter because it goes through the center of the circle J. Since that's a diameter, this has to be a right angle, making this a right triangle. You need to remember that the two acute angles of a right triangle, so not the right angle but the other two angles, have to add up to 90 degrees. Measure of angle F plus the measure of angle H has to equal 90. So the equation we set up is that 4x plus 2 plus 9x minus 3 equals 90. We can combine like terms here and here, and here and here. 2 plus negative 3 is negative 1. Cancel out the minus 1. And divide by 13. And we get that x equals 7. Our final answer is the measure of angle F, though, so we go back to plug that in. Instead of 4x plus 2, we write it as 4 times 7 plus 2. 4 times 7 is 28. 28 plus 2 is 30 degrees. Okay? All right, and then one last theorem in this lesson, and that is if we have a quadrilateral inscribed in a circle, then the opposite angles have to be supplementary. Not congruent, but supplementary. And there's a reason for this that I'll show you in class. We'll come back and look at why this is, but right now just recognize that opposite angles have to be supplementary. That means their measures must add up to 180 degrees. So let's look at our practice. In example 5, quadrilateral WXYZ is inscribed in circle V. We need to find the measures of angles X and Y. This is not very difficult. Remember that opposite angles are supplementary. So the measure of angle Y is 180 minus its opposite angle of 95, which is 85 degrees. And the measure of angle X is 180 minus its opposite of 60. Sorry, my paper's moving. 180 minus 60 is 120 degrees. Because the opposite angles have to be supplementary. That means we take this one away from 180 to find its opposite. All right, there are some things we will come back to and talk about in class. Again, we will do example 3. We'll do this proof in class. It's not super complicated, so don't panic. But we will come back and do that, and then we will start working on the assignment for lesson 10.4. You got that in class. You need to make sure you have started on it before you get to class. And remember that you have a quiz over lessons 10.1 and 10.2 in class on Tuesday.